傻。 他关进去把我那给他干你。
啊，这边。
没啦。
反正我是会打错，找一个位置。
压 Jackson，发 Jackson。
我直接在那边闪开。把这重担交给你。
你要守护这个手机的。
要
开着了。
啊，开照了。
我要看他有没有 focus 到嘛。嗯？还是可以哦。OK。
应该是不用打。
开着哦，10多分钟啊，不然浪费电。
圣洁艾瑞尔。圣洁为什么那么你说一句北宋是圣洁的正宫？
有点烂烂的。有点融了，不一点融了。 好了，哦，哦，只是你那嘛，就好10分钟，还在干预。
This semester is this distributed system and parallel computing. Sorry, I have to use this one because I don't have a loud voice. From time to time, I will use this board. We use Chinese board because okay. I hope you can hear the background of this process. Okay, so we're going to start with what is distributed system and also parallel computing. And then we will talk about real-time system. And the operating system is required to do this distributed system. Okay? So in distributed system we have the left-hand side is this is an example using traditional database. If you have a program that is a web application at the bottom there, and if you access the database, you have only one database and it has to do everything. I mean, the database has to do everything that the web application requires it to do, right? So the whole idea of distributed system for this database is to distribute the task. Okay, so each one of the database has its own task to perform the job. Okay, why we want to do so, this will provide a way to actually lighten up the work. Okay? Let's say you see database 1, database 2, database 3. Database 3 is to authenticate if, let's say, the person who is accessing the web application is the rightful person. Okay? So you can request database 3 to do the authentication. So database 3 is only focusing on that particular job. Now database 1 maybe can be doing something else. Like for example, you want to add new user, you want to delete the old users. We can use database 1. So the task is distributed among all the databases. So each database might have smaller size, and it can be in different parts of the world as well. For example, database 3 can be in China, database 1 can be in Asia, for example. Okay? And not only that, you can perform this task in parallel. Okay, so you can request database 3 to do the job and database 1 do the job at the same time. So in distributed system, you can actually parallelize your work. Okay, even though this is not a parallel system, it's not parallel computing, but distributed system can perform, can achieve a similar effect as parallel computing. Except that in distributed database or distributed system, the system not necessarily resides in one computer, it can be in multiple servers. So this is the basic concept. We want to distribute the computing, okay, into many processing entities, and these processing entities can be any of this. It can be operating system that we want to distribute among the system. It can be file system as well. It can be database. Database is basically just like the file system. The authentication is like what I mentioned to you. Authentication means you want to verify whether the person who access is the rightful person, right? So this has something to do with the cryptography. Okay? Let's say, for example, you go into the website, you have to log in first and you put in the password, right? So that is a form of authentication to find out who you are, whether you have the privilege to access the website or not. Okay, most of the thing will be in the business logic because all your processing tasks will be in the business logic, And these are the heavy work load that you have to support the system, right? So for example, you got 1 billion users using Google. Let's say talk about Google. And if you search for one particular phrase, let's say you go to the search engine, you type in, I want to learn about distributed system. Press enter, immediately you get the results straight away. But you must remember that not only you actually ask Google this question, it can be thousands of people or millions of people asking the same question, not the same question, asking at the same time. So how does Google server able to serve you in split second? Okay, it is not only one server that serves all of us. It is actually a distributed system. Okay, so most probably our request or our search request come from the server at Google in Malaysia. It doesn't need to go to America. Okay, or it doesn't need to go to one specific place. So everybody will be using the server that is closest to us. Okay, it is distributed, it's everywhere. Right, so that is the business logic. The whole idea is to make sure that we can perform the task with the highest performance possible. Okay, the last one, workload, is basically the same as the business logic. Basically the processing, except that this one is doing maybe some processing to clean your database or add into your database. Okay, so this also will have a heavy workload as well, and it is suitable for distributed systems. Okay, the benefit, as I mentioned to you just now, of why we want to do distributed system or distributed computing is basically we want to be able to scale. Okay, meaning that I can start small, but later on I want to scale to a bigger size. Okay, if you put everything in one computer, how are you going to scale? You cannot scale, right? That means your computer, if let's say it's a 4-core, 3 gigahertz, for example, you cannot scale anymore. How are you going to scale? You cannot put better processor in there. You can put a hard disk, more hard disk, but how many hard disks that you can put in? You cannot scale. You can scale up to a certain limit, after that you can't anymore. Okay, but then if you use distributed system, it's unlimited. Because you can have multiple computers networked together, and you can scale as much as possible, right? And if your business size grow, you can scale to accommodate your business. The same thing, you can scale down also. You don't need to scale up only, you can scale down. Let's say your company is not doing well, or you find out that is a burden, and you do not need it, you want to scale down to save costs, you can actually reduce it. Okay? You can reduce the size without impeding any of your existing business logic or work. The second one is reliability. This one is quite important, and we always see the advertisement. People say, let's say for example, you go to cloud services, you buy the service, they'll tell you 99.99999 with so many nines uptime. It means that only 0.00001% that your system is done. Okay? So they can guarantee you up to that point. Okay? So if let's say just imagine that you have one computer like this. If anything that goes down there, you have to fix it. You have to send to a technician to fix it. How many hours that you have to wait? Okay? So using a computer, if a single point of failure, definitely you have to wait. Right? But if you use a distributed system, if it's one down, then you can move on quickly to the next server that is free or less workload to actually cater for it. But of course, you need a way to make sure that you duplicate the data. For example, if I say you share the data, you must duplicate it. If one down, then you can switch to the other one very quickly in maybe split second. You can do it manually, which takes longer time, maybe a few minutes or a couple of hours. But if you want to ensure reliability, like what I mentioned to you, 99.999%, you better make sure that it's automated, meaning that the server is able to sense that something is wrong and then switch to the server that is running. Okay? And the third one is performance. And this one, as I said before, just like the Google example I mentioned to you, when you search, you don't want to wait a few minutes, right? You want to ask Google, and then you want the results straight away. Okay? Of course, it takes some time, but in split second you can get the results. Now, if you have one computer, you are serving 1 billion users, for example, at the same time. Most probably you cannot give the answer in split second, even though your processor is running at gigahertz. You have multiple cores. I'm sure that you're not able to serve all 1 billion users requests at the same time. Okay? But then if you have a distributed system, the server is very close to us, okay, only serve a few customers, each for each server, and you've got thousands or millions of servers doing the same thing, then you got performance enhancement. Okay, the last one is geographically distributed processing, and this is good because you do not want your assets to be in one location. You want it to be in Malaysia, you want it to be in Japan, in Australia, in America, or whatever countries that your company accesses. Okay, and it can be a good point as well for this kind of geographically distributed processing, because for example, if let's say you have your main office, your headquarters is in Japan, right? What happens if there's earthquake? If there's an earthquake, not only one server is down, the whole server farm will be down, right? So if let's say you have another set of server in America or in Malaysia or Indonesia or Thailand, for example, then now you have the data that is still able to serve people, even though there is an earthquake in Japan, right? So geographically distribute your assets across the world will be a better choice. And also, this will allow you to actually go and open your company elsewhere. Okay, at the same time, share the data. Okay, you don't have to everybody have to go back to the headquarters in order to do their job. Okay, so they can actually do their job at their own country. So this is benefit and scalability, and I know that this graph has something related to the previous list, but then it has a certain note inside here, which I think I stress a little bit. Here, when it's talk about scalability, they actually try to compare two things. Try to compare vertical scalability, which is the dashed lines, and then horizontal scalability, which is the black line. Right? What is vertical scalability? Vertical scalability means, if let's say I have a computer, right, and then I need to improve my computer right now because I have more customer to serve. So what do? I add more memory, I add more hard disk, and then I improve my core, I change my core to a better core, for example. Right? So this is vertical scalability because I scale the existing computer, right? So that is vertical scalability. How about horizontal scalability? It means I don't improve my computer. My computer is an old computer, it doesn't matter. And when I scale, I add more computer. Okay, so this is horizontal. So vertical, that means you improve the computer, or you don't improve the computer, but you add more computer. Okay, so you have two ways to scale. So the graph shows you this. It shows to you vertical scalability. That means you improve your computer, each server that you improve. Your extra capacity that you need, you increase it, and then the price is lower right, initially. But as you reach a certain point, you find out that horizontal scalability is much better. Okay, that means you add more computer, initial cost is very expensive, but at larger scale, like Google size like that, it's better to invest in horizontal scaling rather than vertical scaling. That's why you see Google don't invest in supercomputer. Supercomputer is vertical scaling, right? Horizontal scaling, that means you add more server inside there. You see a lot of server inside the server farm, right? So Google are doing that, but in the past, of course, we don't have horizontal scaling because it's very, very expensive. You can see the initial cost is very expensive and computers are very expensive. So most of the old companies, when they begin, they always do vertical scale. Okay? Just like our PAR UMP, last time we are PAR College. Now the lab that you're in D block, we already upgraded. Actually, we have personal computer that, but before that, when I was a student, I was in Harvard as well. And we have one computer. It's a mini computer. It's like a smaller supercomputer. And everybody is using that computer. Okay? It has a terminal. I mean, it has multiple terminals and keyboard with the screen. But then we are actually sharing the same computer. It's called mini computer. Right? So if in the past, they have to do that because one computer is very expensive. It's like millions. They have to spend millions just for the computer. So it's not so cheap. But nowadays, everything become cheaper. So most of the company that we see is using horizontal scaling when they want to increase the capacity, okay? Because they have a lot of saving here. You can see the price does not increase exponentially, but it increases kind of linearly. Okay, so the thing I thought about, we have a lot of benefit, of course, but what are the challenges of this distributed system? Okay, there are challenges. The challenge is how do we replicate it? We need a way to replicate it, right? Of course, replication is easy, but you have to coordinate all this replication, and you need to know where you want to replicate it. You cannot just simply replicate. You need to know where you want to replicate. Just for example, Netflix. Netflix also use distributed system, okay? And whenever it sends a video to you, right, it doesn't send from the headquarters. Let's say headquarters is in New York. If everybody is going to watch the video from New York server, although it has a lot of server there, it's a horizontal scaling, but how about the network? The network in America will be very busy, right? Because you have to serve all of us, traffic coming from us, from around the world, okay, getting the video from one place, New York. Okay, let's say for example, and it's not good. So how do we do replication? Netflix, of course, they do replication. They know that I watched the video, and they also know that some of my friends, or some of the people who like that kind of movie, will be watching it as well. So it will send one copy to the server close to us in Malaysia. One copy, so you get replicated. Okay? And then we, as a viewer, initially perhaps our video come from New York, but after a while it knows that other people also watching. It will send one copy to a server nearby us, so that this copy will be shared among my friends who's watching the video as well. Okay, so the traffic doesn't come from New York anymore. It comes from New York one time to the server nearby in Malaysia, and then everybody will be accessing this video. So the replication is according to where the demand is. Of course, I don't replicate everywhere. If I replicate everywhere, I waste my hard disk space, right? So I only replicate when it is needed. So the idea of replication here is simple, but how do you do it? Okay? So there must be a way to actually find out what is the best way to do the replication. Okay, so another thing is how do we create availability? That means we don't want to show to the customer that they have long downtime. Okay? Availability here means maybe my server is down. I need to quickly switch to another server, or I have to service my server because after several years, maybe dust is accumulating inside there, it's not performing well, heat, the processor heating up so badly that it has to slow down. Now I have to send in technician to go and clean it, right? So you need to make sure that when you turn off the computer for service, you must make sure that the customer don't see this. When you turn off, the data is gone. You don't want that, right? So you want to show that the availability is always there. So somehow you have to move the data or the processors that's running on that computer to another system, so that it can still serve the customer, okay, without degrading the performance. Okay, the third one is in the distributed system. When I use it, I don't want to see it as a distributed system. For example, I go to Netflix. When I watch the video, I just browse to their website. I go to their website. I go to one place, the website. Okay? But then when the video comes, the time when it gets streamed, it may be the server comes from Malaysia. Okay? So the IP address has already changed, but you do not know it, and you do not need to know it. Okay? And the Netflix also don't want you to know it. Because if you have to know, then your job, your user experience become pretty bad. Because right now you have to figure out which server should I go to, right? So in this case here, the addressing the location of the resources should be transparent, meaning that the users do not need to know all this, and the server, whenever the server change to different location or the IP address has already changed, it will do it automatically without you knowing. Okay? Actually, the last one is the same as the second last. It's basically binding means you bind the address. For example, initially the IP address is the headquarter, and then when you are receiving the video from the server nearby you, and then your IP address will be bind to the new location. Okay, another thing that actually the slide is a bit messy. I was talking about what did I talk about? I talked about benefit, and then I talked about challenges. Then I'll come back to benefit. Okay, the benefit. One benefit of distributed system is fault tolerance. In fact, I already mentioned it a few times. Fault tolerance means in case of downtime, in case the computer is down, okay, you have some other server that is going to take its place. Okay, it will do it automatically. It will switch it on automatically. Okay, but with the hope that the data is still able to be saved. Okay, but sometimes, if let's say earthquake, your data is in Japan, then earthquake, all data is lost. You have to start all over. But what they can do is this. Before they know that earthquake in Japan is very frequent. So what they do is they replicate your data first. So whenever you update, you replicate it somewhere else, right? So let's say there's an earthquake happen, then your data is still available elsewhere. Okay. So of course there are many ways to solve this. This is you have to plan ahead. Okay, you have to see the situation. For example, in Japan, you know that this kind of thing can happen very frequently. Right? Either you make sure that your server, whenever there's earthquake, still survive, or you do this kind of replication, like I mentioned to you. The replication ahead of time, just to make sure that the data is not lost, even though earthquake is really disrupting the data completely, destroy the data completely. Okay, another one is low latency. Low latency is the example that I gave to you just now was Google, right? If you are relying on one computer, then you have to wait. But if you have thousands or millions of servers doing the search for you at the same time, for everybody, then it will be low latency. Latency means delay. Okay? By the time I press enter, and the time I receive the result, that is latency. How fast the result comes back. Low latency means it is fast. Okay, so how do we build this computer? I was talking about distributed computing and all that. But how do we build this computer? We are not talking about one computer. Of course, one computer is easy. You just go to the shop and then you get one computer. But if you are talking a distributed computer, you talk about either the computer is upgraded vertically or upgraded horizontally. So how do you upgrade? There are two ways. One way is to do tight coupling, tightly coupled hardware architecture. The other one is to use loosely coupled hardware architecture. Okay? Tightly means it is kind of tight. Loose, as you know, is loose. Okay, the top one is tightly coupled processor. And this is, let's go to the slide because I can't remember where I used the slide. Okay, tightly coupled. The processor is built onto the board itself. Okay, and it has a fixed number of processors. You cannot change it anymore. Let's say IBM come up with a motherboard, and it has 16 processors built onto the board. Now when that board is sold to you, you cannot change it anymore. Okay, so it's fixed architecture. And normally this one is specialized, so if you ask the company to do it for you, let's say for example IBM, you ask IBM, can you develop for me or develop specially for me? Then it's going to be expensive because it's not a common commodity, not like a PC that you buy from Dell and all that. Dell can make it cheap because it is common commodity. It sells to everybody, right? So a larger scale of production can drive down the cost. So if you buy only a few and you need somebody to develop, design, and test for you, that will be very expensive. Okay? So this is something to do with economy of scale, meaning that if you produce in large quantity, you can drive down the cost. If you produce in low quantity, you cannot drive down the cost. You have to sell at very expensive cost. Okay? So tightly coupled normally are specialized hardware. Fixed architecture, once it's designed, you cannot change anymore. You can change, but you have to pay extra money. Okay? And it's expensive. And the number of cores is limited. Limited to how many that they can support on one board. Right? So if you want to scale it a lot larger, normally you can't. Okay? You have to either go and find specific processors with multiple cores. Okay, nowadays we can produce, I can't remember, I think 512 cores inside one processor. And the size of the chip is as big as this, one chip itself. Okay. So it's very, very large. And it's also very costly. Okay, there's one company called Ampere. The company produces processors with 112 cores. Okay, that kind of cores are very expensive. As I said before, it's tightly coupled system, but it's going to be expensive. Okay, one thing good about it is that now the clock is synchronized. Okay, you see this very often. Why clock is very important? Because you need to do some kind of synchronization. When you do the work, especially when you do the work in group, you need to know when to start, when to stop, and when to pass. When you pass the data across, you need to make sure that the person do the job at the correct time and return it back to you. Okay, so the synchronization is very important. And for tightly coupled system, it comes almost free because everybody shares the same clock, right? So everybody sees that same clock and they don't have to worry much, okay, about the synchronization. Another thing is this tightly coupled system normally have shared memory, fast shared memory. So even though you've got 16 cores or 64 cores, your memory can be terabyte or petabyte. Okay, tera is 10 power of 12. Okay, then peta means 10 power of 15. Okay, so it's quite much. Okay, that is memory. Or you can have a shared storage, which perhaps even bigger than that. Okay, this one activity, I think all of you have seen this before. I won't go into that. I'm sure about it is here also. Okay, let's move on. We need to wake you up on it. Alright, so let's look at the loosely coupled system. Loosely coupled system actually is similar to horizontal scaling. Right? And you have separate computers. That's why it's horizontal scaling. Just not tightly coupled is more like a vertical scale. Okay? This one is more towards a horizontal scale. So loosely coupled, you use multiple computers. You connect them through network. Okay, and the reason why you do that because is like for example, if you buy the computer from Dell, it's going to be cheaper than you buy from IBM specialized for you, right? And you can actually buy more of that, and you can compete with the price. For the same 16 cores, 16 processors, maybe it's cheaper to buy from Dell alone, okay? Or maybe HP or whatever company that produce a computer, reliable computer. And it is a bundle. You can buy anytime because it's already there, off the shelf. If you buy from IBM, you ask them to design, it takes time, maybe half a month, 1 month, 2 months, or half a year. It depends on the complexity of the hardware. Okay? Before I go on, maybe I'll tell you a little story of Google. Google was found by two students in American University. While they are in a dorm, they were figuring out how to actually serve customer just like Yahoo. Okay? Yahoo, you all still know Yahoo, right? Yahoo used to have similar kind of search engine where whenever you want to find resources, you go to Yahoo and then they'll look for you, give you the link to the resources that you want. So Google tried to do something similar, but slightly different from Yahoo, because Yahoo is not well organized, and you have different kind of categories. Let's say you like to shop clothing, you go to the clothing section and all that. So it's kind of messy. And Google tried to simplify. That means you go to search engine, you type in, you find everything for you. Okay? So when they started out, they do not know whether the idea will work or not. They are poor, they are students, not to say very rich. And what they did was, they used loosely coupled system. Right? That is the obvious way. If they try a tightly coupled system, if the business does not grow, then they lose money, and they have to lose a lot of money, because if you want to create tightly coupled system, you have to spend millions. But loosely coupled system, what they did, they just go to second-hand warehouse. They go and look for computers that is already being used, and people sell it at cheap. So they buy all these computers, go back to their dorm, and then they construct it, they build it, put internet connection, and run the program. Run the server. Okay, so that is how they started. They started with a loosely coupled system. Okay. So they scale horizontally to find out whether the idea works or not. And they can do it very cheap because they don't have to buy new hardware. The hardware is abundant everywhere, and they can buy a second-hand one. People do not want it, right? For example, you can sell, you can buy maybe 1/10 of the actual cost. Okay? They do not need a super high, powerful computer. In order to scale, they just add more. Okay? They don't have to get one computer super fast. They just get a maybe moderate or low quality computer, and then they scale. Okay? So that's how they got started, and now they're billions, company with billions of investment. Okay, so the loosely coupled system has one disadvantage of loosely coupled system. It has no synchronization because it does not share clock. So this is the problem. Okay, sharing clock here is one thing, but doing the job and synchronizing, knowing who is doing what, when, okay, is kind of important, because otherwise you are not going to be able to do the work properly. Okay, just to give you an idea, some systems require clock synchronization, very precise clock synchronization. Let's take, for example, your GPS. Your GPS actually use very, very accurate clock, and it's in fact we call atomic clock. Okay, that clock on one satellite and the other satellite, the difference is in maybe picosecond. Okay, picosecond is 10 power of minus 9. So that is how accurate it is. Okay, and why it needs to be accurate is because GPS works this way. Let's say you got your handphone, right? Your handphone, and you're at one particular location. The GPS satellite actually sends beacon, and that beacon has clock, right? And when you receive from each of the satellite, and you compute the time difference, and time difference will tell you your location. Okay, I'll just give you some idea how GPS works. Just to give you an idea why time synchronization in some systems is very important. Let's say this is satellite. Of course, I draw in 2D. It's 3D, right? Okay, let's say you're here, and then there's another satellite here, there's another satellite here, right? So you're here, and you receive the beacon from this satellite, and from this satellite. And you notice the distance is different, right? And the signal that is sent actually travels quite very fast. It's travel almost at the speed of light. Okay, there's a radio wave. It's travel at around 300 kilometers per, sorry, 8 meter per second. Okay, so it's very fast. But then this one, remember, it comes from satellite. That means it's very far away in outer space, right? I mean outside Earth. But then it's orbiting the Earth. It's kind of far. Okay, so this distance here and this distance here can be quite large distance. And then when it's sent the time of that beacon. The same thing, this can also send at the same time. So by comparing the time difference, then you can find your location. So you need at least three satellites in order to find your location. And that's how your GPS knows your location. Okay? Because this is nearer, so you can find out, oh, this time is faster, that means it's nearer to this. Okay? So basically, you do something like this. Okay, we do something like that. So anything on this ring here, you must be on this ring here, because from the time, your own time and the satellite time, you can estimate how far are you from this satellite. So you're over here. Then you receive here, from this, you must be in this ring. Okay, if you are receiving from here, on this ring. So the one that is overlapping is the location where you are. Okay? So that is how GPS works. And that timing is very important. If you off by a little bit, your system might think that you're here, is or here. Okay? So with precise timing, then only you can get to this location. Okay? Nowadays the GPS from China especially, they have their own radio sponsor line. That one, the error is 1 centimeter. Okay, the error is 1 centimeter. If you are using the old GPS by America, the error can be 5 meter to 10 meter. Okay? The latest one, we can go down to 1 centimeter. 1 centimeter is very, very small. Okay, so some systems, not all systems require time synchronization, but some do, and those will have some kind of requirement, depending on the application. Like GPS is extreme case, it needs to be extremely precise. Okay, the motivation for loosely coupled distributed system, the interest in it grown because you need to share a large amount of data. As nowadays, we all know that we share a lot of data, right? For example, Google search engine, it needs to share the data so that all the servers that is serving your request will ask this main server, and this main server need to share this data, otherwise you will not get the search result. Okay. Another thing is availability of cheap workstation. So loosely coupled is very popular. One example is Google. Okay, they can buy second-hand hardware from any warehouse that sells at very cheap price to build a system. Okay, they don't have to go to a specialized company to build expensive tightly coupled system for you. Okay, and the third one is the need to share expensive peripherals. Okay, let's say for example you have a sensor which is very, very expensive. Let's say for example quantum computer. Have you heard of quantum computer before? Okay, quantum computer is built by Google, it's built by many universities, and I can access into their quantum facilities. You can access as well. You go to their website, okay, and then you can write a program and submit as a batch. I will execute and give you the result. Okay, but it runs on quantum computer. Okay, so that is expensive, and not all companies can afford to have it, or maybe do not have the technology or the knowledge to build one. Okay, so with this you can share your expensive resources, especially your resources that is hard to acquire, or you don't have the capability to produce one. Then this loosely coupled system is very, very useful, or it can make things happen. Okay, and the last one is you have very cheap high-speed network. And nowadays, I think everybody is talking about, of course, wireless megabytes, maybe gigabytes already. In the future, maybe terabytes. So it's very cheap now. You have to pay much in order to get to that, to get that capacity. So distributed system become popular because of that. Okay, because tightly coupled, you don't need a network connection, right? Because it's all on the same system. But when you do distributed system, your distributed system can be everywhere in the world. You need to have a good connectivity. Okay, another motivation for going into loosely coupled distributed system is that you need to have a local control, so that you can prevent hackers from hacking into your system. Okay? So you, of course, you need to get somebody to do this authentication job and all that, right? Okay, another one is you need to communicate and interact. Okay? So distributed system will be, in this case, because it's already dispersed around the world, it needs to communicate and interact. Okay? And you can scale easily using loosely coupled compared to tightly coupled, because it's just add in computers. Okay, and also like what I mentioned to you, most of the service from loosely coupled system widely used, especially Amazon, also doing the same thing. In fact, all companies, Alibaba, Amazon, Google, are using loosely coupled system because all users want realistic response time, very real time. Whenever I request certain tasks to be done, it can be done instantly. Okay, this is the distributed system. Of course, we have a lot of servers. These servers are describing the processes. And you are connected using network. And you can have a distributed system using processor. You have processor on the rack. slightly more expensive. I think Amazon is using this. I think Google also using this now because a bit richer now compared to the past. And these are still easily available, although they are kind of specialized for server. Okay, because server farm is very popular nowadays, and not only Amazon is doing that. Many small companies are doing that. So a lot of companies are also producing servers that do not have monitor, do not have keyboard. It's called headless computer. Headless computer means there's no monitor, there's no screen, there's no mouse. Okay? They only have the processor and it is kind of naked. It does not have a casing. You just put it into the rack. Okay? So it's kind of cheap also because it's a common commodity for server category. So that will be the proof processor. And there's another one, I think I'm not sure, maybe I missed it. It's Greek computing, I think it's this one. Greek computing, this one can scale better than the pool processor. Greek computing, the idea is slightly different. It does not need to have this pool processor, this specialized processor. It can be a computer. Okay? Greek computing is, if you want to see an example, maybe SETI. Have you heard of SETI? SETI is to scan the sky, looking for signal, but because the data from the sky that they receive is very huge, they cannot compute using one computer. So what they do is they ask people like us, normal users. We register, you can register to SETI. So if you register your computer to SETI, then SETI has the privilege to send the data to your computer and the program to your computer, and your computer will process the data. Okay, that means as a background task, not the main task, a background task. Okay, after processing, you send the result back to SETI. So basically, SETI is taking advantage of many computers around the globe in order to do computation for them. That is Greek computing. Okay, and this is very massive. And what SETI is doing actually is to find the signal, maybe UFO signal from outer space, because most of us believe that there's a UFO somewhere. Maybe they're sending signal and we don't realize it, so we scan the sky and look for some kind of pattern, signal pattern. But in order to scan them, it's too large, they cannot do it in a single computer. That's what they're doing. Another one is biogenome. Biogenome, let's say for example, they want to find medicine, right, to cure certain disease. And of course, you can go to the lab and test different kind of protein or whatever. But that takes very long time. So the idea is to use simulation. You simulate the molecules, the behavior of the molecule, how they interact with other molecules, to find medicine for one particular disease, for example. But this computation takes very long time because there is no perfect way to actually find a solution. So what they do is they also go to Greek computing idea by asking all of us to sign up so that we can share our computing power as a background computing power, so that they can send the data and the program to do the processing of computer and send back the data to the program to check if that data that we compute actually has some kind of solution useful for them. Okay? So Greek computing has a lot of usefulness, especially in this kind of work, where they don't have money to buy a computer, but they need a lot of power for certain purpose that is useful for humanity. For example, medicine, right? So it's not only that they get advantage from it, they don't want to share this medical product to all of us. And we are the one who actually support them and we get the benefit from that discovery. So that is Greek computing. Okay, just now I talked about a little bit about transparency. What does transparency mean here? So distributed system presents a lot of challenges to the developers. The first thing is the developers need to think where to put the process and where is the best place to put the process. Can you put it in one place, or it's better to put it in another place? So you have to think about it. Now, once you place that process on certain computer, can you move it? Okay? Let's say, for example, you are doing some work here. Okay, it's still processing there. Then can you move it? Why do you need to move? Maybe you need to maintain it, or maybe something is wrong. You have to move it quickly. But how are you going to move it while it is still running on the computer? They are doing hardware. Okay? So they have to think about all this. The developer have to think about this. Can we do that? Next is when we put the data or the resources. Okay, data and processor are two different things. The processor is the one that compute. Data is where the resources is, where you get the data to do your processing, right? And can you move the data? Data is much easier to move than the process, but then it can be large, right? So we tend not to move if the data is large. Let's say in terabytes, we don't want to move it. We want to stay at one particular location. So if we want to move, how are we going to move so that the user don't feel it? Transparent means the user don't feel it, right? When you move, I don't feel lagging. I don't feel like, oh, I have to wait for 1 hour because of this move, right? So how do you do it? Maybe you want to do it this way. You have to move 1 terabyte of data. But if you move 1 terabyte of data, you have to ask the user to wait for 1 hour, for example, or a couple of minutes. But then what you can do is maybe you move a little bit, right? The one that is being used. And then once you move, the user is using it without knowing it. And then you move the rest of the data that is not being used at that time slowly. Okay? Whenever this data is being touched, is being used, then you have to transfer it immediately. The rest that is not touched yet, you delay it, so that the user don't feel that kind of have to wait for the latency due to this kind of thing. Okay? And the third one is to provide robustness. Robustness means it's hard to fail. Okay? Let's say, for example, I have a computer in, let's say, Japan, an earthquake. If there's no robustness there, that means I have to start all over again. Okay? But if you provide robustness, I can immediately switch to another part to counter this failure. So the user don't feel it. Okay? While it is processing, maybe the processors was running in Japan, and then there's an earthquake. But then my process immediately get transferred to Malaysia, for example, which do not have any problem. And then the user, when he is using it, he doesn't even know that the process has been transferred. And he doesn't even know that it was the server that it was using earlier on has been has been damaged by earthquake, for example. Okay? So this is robustness in order to counter a failure. And also to ensure consistency. For example, when I do some banking, let's say the database do the debit credit of my account, for example, right? I withdraw 50 ringgit, but when I withdraw the 50 ringgit, the server actually break down. Okay, but I replicate my database, right? So when the system switched to another server, that server is actually telling me that I have the extra 50 ringgit, even though I already withdrawn. So this one is consistency, and this is very bad for bank, right? Bank do not want you to have more money than what you deserve, right? So consistency means the data is consistent throughout, no matter what happened to your data, whether it's corrupted or not. When it gets the data gets moved to somewhere else, and you don't see any change there, but then the data must be consistent. Okay, so transparency, part 1 is that. Okay, part 2 is how do we make sure, just now we're talking about the developers, how we're going to deal with all this. Now we're talking about the user experience itself. It means hiding of details of the distribution. That means if as a user, when I go to Netflix, even Netflix is everywhere in the world, it's distributed, I mean the server is distributed all over the world. But then when I access Netflix, I go to one website only. And when I watch any video, it's actually from that particular website. I will be thinking that I will be accessing the main website. But then all the data actually come from all these distributed systems. So Netflix was able to hide all these details from us. So that when we use it, we don't realize that our data come from a different part of the world. Okay? So this will reduce the burden, not only for the developers, but for the user as well, because user don't have to know where to look for the data. Okay? Okay, the transparency also to account the access transparency, like what I mentioned to you. I do not need to know whether my data or the objects that I'm accessing is local or remote. Okay? And I don't need to know where it is, whether it's Japan or in Malaysia. Alright? And also, I also do not need to know whether anybody is using at the same time as me, because everybody might be using Google search at the same time, but they don't have a field or get interfered by my search. Let's say when I search, it doesn't slow down other searches. Okay? So this is concurrency transparency. Meaning that if I search, somebody else search, I don't affect other work done by the system, on other part of the system. Okay, replication transparency, like I mentioned, if I say we know that one particular place is prone to earthquake, then you better do replication, and the replication needs to be transparent. Meaning that when you replicate, I do not need to know it has been duplicated. Okay, there's one case. Another case is Netflix, where when I watch the video, initially it maybe come from New York. Then when I found out that a lot of people in Malaysia is watching the same video, so it's best to send one copy to the server in Malaysia. So this replication is done without user knowing it. Okay, and then the streaming from the video, initially from New York, eventually it will be passed over to the server in Malaysia. And when this transition happened, the user like me will not know. Okay? As I watch the video, I think that it's coming from the same place. It actually has already has been replicated, and the video streaming actually comes from the server which is close to me. Okay, flag failure transparency, I've talked about it many times. When there's a fault, the system automatically switch to another place without user experiencing it or knowing the fault has happened. Okay, migration transparency means I need to migrate. For example, I need to service the server, so you need to migrate. Okay, you have to migrate two things. First, the process. The second one is the data, or both. Okay, data is much easier to migrate. Migrate that means move. Process is harder to move because when you do halfway, then you have to move to another processor. It's kind of hard, right? But it can be done if you use a certain protocol. And I think we're going to learn in chapter 5, if I'm not mistaken, on this migration transparency. Okay, performance transparency is also the same thing, like what I've also already mentioned. If let's say the load increase, what you need to do is you don't tell the user, okay, I'm sorry, I cannot serve you anymore, right? User don't like to see this kind of message. But what you can do is you share the load, but you degrade a little bit the performance to cover or to cater for more customer, increasing customer. So your performance degrade a little bit, okay? But you don't tell the user, I'm sorry, I cannot service you because overloaded. So that is performance transparency. And the last one is scaling transparency. So when I scale the computer, let's say Amazon is scaling the computer. In fact, Amazon and Google keep on scaling their system, but their system is always up and very few downtime. So when they scale, they can just add computer without switching off my system. Okay, my system is still running. You just add in to scale the server without me knowing it or without me having to suffer when they do the scaling. Okay, next we move on to another topic. Just now we talked about distributed system. Now we talk about the real-timeness of the distributed system. Why do we need it? The real-time distributed system, in fact, in your car, in a modern car, you are driving a modern car now, right? Your car actually has a lot of processors inside there. I'm not sure whether you know. It has people counter, as a BMW, I think about more than 50 different processors in there. Okay, it does not need to be a powerful one, it can be less powerful, but there are a lot of processors. That means there are a lot of processors handling one particular job. Like for example, the braking system is one processor, the engine itself also one processor, and then the one that control your tire, the braking of the tire, one processor, and then the back that to protect you when you have accident, there's another processor, okay, to actually compute and also detect and to blow up the balloon so that you don't get hurt. So there are many processors in there, I think about 50 over or maybe 100 over processors in there, just to do computation. Okay, and real time is important. For example, when you get into accident, right? The airbag that is come out to protect you need to be fast. If it is responding very slow, what happens? Maybe it doesn't save you at all, right? The bag come out, already you hit the dashboard, it's too late already, right? So real timeness here is very important. Another one in airport, also the same thing. Okay, because just a split second, things, catastrophic things can happen. Just recently in Japan, I think there's a problem with the visual problem, where they do not see the plane. One plane coming down, the other plane is going to fly off, but they're on the same lane. Okay, because miscommunication and they cannot see one another. So when the other plane, the Boeing actually came down on top of the other smaller plane. The plane that is the bigger one, luckily a lot of people, they all are unhurt, but the plane underneath, all passenger died except one captain. Okay, so even a split second of mistake, there's no time for you to actually make this mistake unless you have real-time system to actually give you this kind of time, right? But of course, that one nothing to do with real-time. But if let's say there's a real-time system there, it can tell you immediately that there's a danger that is ahead of you, and you have to take a precautionary step or divert. So the typical feature of real-time system is time itself, because time is critical, right? So you need to make decision at that instant of time, okay? In order to get the correct result. Okay, like for example, the airbag needs to be time critical. This is even worse, because your margin of error is in nanosecond. Okay, maybe in the future, maybe 1 centimeter accuracy is in picosecond. So picosecond is 10 power of minus 12 second. So that is very, very accurate atomic time that is installed on the satellite. Okay, and you need to share the resources, communicating with one another. Sometimes you need to synchronize. For example, let's say for example, I go to the bank, I have a debit card, ATM card, and I share the ATM card with my brother. Let's say for example, we share the money, and I go to the bank and I withdraw money. And the other ATM, let's say I go to America, also withdraw the money, right? What happens if he withdraw and I withdraw almost at the same time? If the timing is not taken into account, I might be richer because there's a mistake done by the bank. Because the timing when I withdraw and my brother withdraw almost the same time, right? So they will think, okay, if you got that money, you can withdraw. And my bank in Malaysia, I also was able to withdraw. The one happened in America. So the timing is very important because whoever withdraw, there's a time stamp there, right? They tell you, okay, this money has been withdrawn, so you have less balance. So when you withdraw next, it will be less than what you should earlier on, right? But if let's say the timing is not correct, that means when I withdraw almost at the same time, then there can be this kind of glitches. Okay, so real time is important. You have to keep time correct. Okay, this is to avoid fault and also increase your reliability. Okay? And of course, only specific jobs require this. For example, in this case, and a few examples that I mentioned to you. Okay, and actually this last example is a very bad example. I don't think CD player need any real time, maybe it has. But a more appropriate one is like the airbag that I was talking about, right? Airbag is more time critical compared to a CD player. But it may be also like phone, for example, when you talk, if it is not real time, if there's the delay, then while you're talking, the other person thinks that you are not talking, right? Then you start to talk. And then there will be some kind of confusion there, right? So without real time phone transfer of data, then it can make the conversation very hard, right? I believe some of you might experience this before. When you talk, the other side haven't received it, so they thought that you're not talking. Then they start to talk, and then both are talking at the same time. So that can be a problem, and this is a real-time issue as well. Okay, real-time system very often implemented as distributed system. Some of the reason is because of the fault tolerance. Okay, certain processing of data has to be performed at location where the sensors or the actuator is. Okay, because if let's say your data is processed at very far location, right? For example, of course this is not true. Suppose is we want to centralize it. So the sensor detect you have crashed into something, and then it sends that message to the server, and the server have to compute to find out whether this is real or not. And then if you find out it's real, and then send back to your car, right, through Wi-Fi maybe, then only your airbag, okay, is expanded, but it's going to be too late already because it's not real time, right? So the best thing is to put the processing in near the sensor and the actuator itself. That's why I told you that the airbag system actually has a processor in there. There is one processor. So because of this, because it relies on the real timeness. Okay, when a crash happens, it has to compute it and make sure that that is a crash first before you expand. You cannot just simply expand. For example, while you're driving, suddenly somebody knocked on the car, lightly on the body of the car, and then you expand. That is a very bad experience. Nobody will buy that kind of car. Okay? So here it has to distinguish between light knock and the actual knock that is what do you call it? A car crash kind of knock. Okay, differentiate it, then expand the airbag. And this has to be done real time. Okay? So real timeness will be required for situation where you have performance issue. Okay? If you need performance, right, you apply this real-time, distributed real-time at the particular place. Okay, if it is distributed, that means your communication needs to be in real time. Okay, so no A, no B, basically these are the computers, microprocessor. They are computing their own job or do their own task, and then they share the data. And this data needs to travel to your respective destination at real time. Okay, so you need a real-time communication system. Let's say, for example, in the car, yes, you have real-time communication. Actually, your car actually has a network inside there. Maybe you're not aware. The network is just like internet, right? But it's slightly less powerful. The only advantage it has over internet is the real timeness. Okay, when the data is sent, you can prioritize which message is more important and then transmit that one first. Okay, it's called CAN. If you want to know more, you can go and find out. CAN. CAN is car area network. Okay, specific issue concerning the distributed system is the clock synchronization that I was talking about. Because if you don't synchronize, you will not have a correct idea of what is happening. Okay? And you might have a wrong interpretation of the system. The second important one is the real-time communication that I just showed to you in the previous slide. Okay? If you don't have a real-time communication, then it can give you a bad result. Okay, why this CAN, the current area network is good, is because it has some kind of priority for each message. In fact, your internet nowadays has priority messages that you can send. You can put priority. It's because they follow this CAN. Now, why this is important? Let's say, for example, you're sending a lot of messages, which is not important. It will be suppressed when it sees a very high priority message. So you send that one first. Okay? So that will make sure that the high priority data reach the destination in real time. Okay, having talked about the clock synchronization, how do we do synchronization? There are many algorithms. One of the algorithms to do synchronization, if let's say your system is distributed, is to use Christian algorithm. Now, let me emphasize again, maybe they missed what I mentioned just now. If your computer is tightly coupled computer, then you don't have to worry much about the clock because the clock is shared among all the processors. Okay? But then if let's say your system is distributed, using loosely coupled system where it's connected to the network, then you have to use this kind of clock synchronization. And this one is important, like for example, banking, the ATM machine that I was talking about, one example. You withdraw the money and the bank thought that, because of time difference, they thought that you still have the money balance in there, and you're able to withdraw money again in a different country, and that will give the bank a problem because the bank is actually giving out money more than it should. Okay, so the system needs to find out how to make their clock synchronized. So if let's say the machine, the sending machine, let's say it's one machine. Then this is the machine, and this is the server. Okay? It wants to synchronize with this. So this is the sender, this is the time server. It wants to synchronize to this time server. Okay? So how does it synchronize? Maybe we can think of like this. I ask you the current time, and when you reply that time, then I use that time. But you must remember this. When I send a message, the message needs time to actually travel. Okay? Let's say I'm in Malaysia, this one is in Russia. Okay? Even though the message can travel quite fast, but it needs time to actually send, receive, process, and then return back. Okay, so there's a time that is going from machine to the time server. Okay, so that is, let's call it T1. Okay, and there's some delay that is coming back here, T2. Right? Okay, so let's say I request, I'm the sender, I request. The message takes time, takes this much of time, okay, to reach here. And then when you receive, you look at his own time and then send a message. Let's say the time is showing me 12. Okay? Exactly 12. 0 seconds. Alright? But when I send here, let's say for example, when I send, my time, maybe my time is very off, let's say 10 o'clock at the time. Okay, let's say my time is like this. Let's say my time is off. Right now I want to synchronize with this accurate time, and I send a message. I know when I send, okay? And then when the message appear here, I can see the difference there right now, right? So the difference is 12 minus 10. Okay? So I know the result here, but I cannot use this result. I cannot use this 12 o'clock because of this delay and that delay. Okay? So what I do is I time. I find out when does it come back. When it come back, let's say it come back 1 minute later. Let's say this is a very poor network. It come back at this time. Okay? I send at this time, I receive at this time, and I receive this value. Okay? So I know that the time difference here is 1 minute. Okay? Now we assume that in Christian algorithm, we assume that the path that is taken here and the path that's coming back is the same path. So the delay that is going and the delay that is coming back is the same delay, right? Because it maybe go through the same path, right? So let's say if I look at this, it means that how long does it take here? It take 1 second. So that means when you reach here, there is what time? What time does it reach here? It reach here in half a second, right? That's what, half a minute. And then come back 1 minute, right? Because it's 1 minute, right? So it reach here is half a minute, okay? And I get this time. So what is the time that I should change to? What is the time that I should change to? What's the time that I change it? My time is this, when I send. It takes half a minute to go and half a minute to come back, assuming the same time. And the timestamp that is given in the message is 12, exactly 12. So I have to change my time from this to what? What's the time that I need to change it?
12.
Half a minute is 12 o'clock. Coming back is another half a minute. So what is the time that I need to change to?
12.5.
Okay, if you don't know, actually the answer is down here. Okay, that is the answer. Right? Okay, T record is the time that is T record, right? And then transfer is, that means this delay, okay, that delay. Okay, because the transfer is, as I told you before, we assume that going and coming back is more or less the same, right? So meaning that when I get the transfer time is, let's say 1 minute, then I divide by 2. Divide by 2 meaning that it takes only half a minute. In this case, half a minute to get there, right? So the time that I need to change is the time that I get there plus the difference divided by 2. Does it make sense? Okay, so that is the time that I need to change to. So the idea is actually very simple. It's just to compute the time difference and divide by 2. Then I can estimate what is the time that I need to change to by taking into account the delay in the network. Okay? So that is the formula that we use. C, which is the current time, and then you subtract the difference divided by 2. Okay, so we don't do this because if you do this, that means you are not taking into account the transfer time. Okay, Kristen algorithm problem. What is the problem? Network delays are time varying. That means even though you take the same path, going might be different from coming back. Okay, even though it's the same path. If it is different path, that is even worse. But if let's say we assume that going and coming back is the same path, but we still have problem because the network delay depends on how heavy is the traffic, right? So you might be using MR2, let's say for example, going and coming back in the same MR2, but then you can see one side a lot of traffic, the other side no traffic, right? So it depends on the amount of traffic on one particular day. So even though you take the same route to get to your destination, or coming back from whatever destination you come from, that means you go to, that will depends on the network delay that is caused by the traffic. Okay, so Kristen algorithm has this problem. We assume that going and coming back is the same because it takes the same path, which can be quite likely. But then network delay can be time varying. Okay. Second problem is the network delay can be different on each direction, even though on the same path. I have mentioned just now. Okay, it's not even. Just like, for example, when you use your mobile phone, right? You use the data plan. Do you know that your download is faster than your upload? Your upload speed is slower than your download. Okay, so this is the problem that is talking about. Okay, the third one is processing delay. Because when, of course, we are only talking about the network delay, but how about the processor itself? It also takes time to process, right? Read your message, and then read the time, and then package the message, and then send it back. Of course, you can do it very fast, but you cannot get to certain precision. If you are talking about nanosecond precision, don't go for it. If you are talking about millisecond, maybe okay, is doable. But if you are talking about microsecond or nanosecond, completely is out of question. Okay, because your computer is also running at that speed as well, unless your computer is running extremely faster than that. Okay, so that is a Kristen algorithm. The next one is Berkeley algorithm. Okay, they are clock synchronization, but the focus is different. Just now, the sender tried to synchronize to the time of the server. Okay, they tried to synchronize to this time. That means he tried to estimate from this communication here and there, even though there's the delay. He tried to move its time very close to this time server. Okay, synchronize it to time server. But not all applications require this kind of synchronization. Some applications you do not need to be synchronized to the server. What you need is everybody in a group has very, very close synchronization of the time, even though it's out. Okay? Even though it's out, but then you want it to be synchronized. What I mean is this. If you look at accuracy, this is the target. If you are here, it's out. If you are here, high accuracy. Right? Okay? Now, how about this? This is accuracy. Accuracy means this is the target, or I should circle there. If you are here, that means you are not accurate. But if you are here, it's accurate because this is the target. Now, suppose this is the target, but you don't care much about the actual target. You care whether everybody is very close to one another. So let's say, for example, you get something. Right? So if we talk about accuracy, the accuracy is quite critical because you need to be here, from here. But if you talk about precision, yes, because everybody is around it. Right? So Berkeley is actually focusing on this rather than this. Of course, they try to get into here also, but then the focus is on here. Whereas Kristen algorithm, you want to get to this target. Okay? And why Berkeley idea is this? Because it's easier to do this with precision. Okay? Compared to Kristen algorithm trying to get to this accurate time. Okay? Sometimes you do not need the time to be accurate, but you need the time to be relatively accurate among yourself, right? So you use this particular algorithm. How does it work? You work like this, the master, to make sure that every of the slave, there is only master clock, make sure that everybody around it must be very accurate. I should say not accurate, I should say precise. They need to be precise, doesn't need to be accurate, right? So how does it do? First, just now, Christian, the sender, sent a message to the time server, right? This one, the master sent to every of the slave. So it's the reverse. Okay, who actually initiated is different. Okay, in Berkeley algorithm, the master sent the message to the slaves. Request for the time of the slave. The slave is not the worker. We assume that is a worker. Okay, and the slave will return his own time, and the time can be different. And what the master do is, he has his own time, right? So you take the difference. The difference here is 10 minutes. The difference here is 20 minutes. The difference here is 50 minutes. The difference here is another 10 minutes, minus 10 minutes. Okay, you take the difference, positive 10, positive 20, minus 10. Okay, and then divide by 3. Okay, you divide by 3, and it has that difference, and then you add to the clock, and then you send this clock through plus the average that you calculated, and then send to all the slaves. Okay, so the slave right now will receive that, and the slave will adopt that value that the master sent. Okay, by doing this, now the algorithm is simpler because your focus is actually to get precisely the synchronized value, not accurate value, but precision is important here. So this is the algorithm that is inspired by Berkeley algorithm. So it depends on your application. Your application need accuracy, then perhaps you have to do this thing algorithm. But if your system require precision rather than accuracy, then you look at Berkeley algorithm. So it depends on how your application use the time. Okay, whatever I mentioned just now is here with the code and all that. You can see yourself. Okay, get the time difference, sum all the time difference, divided by the number of slaves. Okay, that will be the average time. It can be positive, it can be negative. And then you use that you add it to your the master time, and then you distribute it. Okay, this is the last part. Lifetime. I finished at 4, right? Okay, the last part is operating system. And of course we have, just now we talked about distributed system, why it's important, what are the challenges, what are the benefits, why you want to use it, some example that I give to you. Then I talked about real-timeness and the time that is quite important. Not all require time, but some application requires time, so you need to be real-time when you do distributed system. Otherwise, the system will not function properly. Okay? But of course, if we don't talk about distributed system, then normally we don't worry about the time. Why? Because if you work on the same computer, you don't need time, right? Because you know what process comes next or before. Okay, but when you're doing distributed, every system is working independently. So right now you have to synchronize. So you have a new problem that you don't have on a single computer. Okay, so that's why we have real-time problem. The last one is the distributed operating system. Because right now you're not running one operating system. You run on multiple systems, and this multiple system has their own operating system, right? Of course, you can run Windows, which is not the distributed operating system. Then you have to add on application in order to do all this synchronization. But then if you use distributed operating system, this distributed operating system provides you all this facility without you needing to know as a developer. So it becomes transparent to you as a developer. So what does the operating system do, the distributed one? It can schedule the tasks on different computers. That means across the network, not only on one computer. So it can schedule, just like the normal operating system on a PC. It can do the communication without you needing to know that you're communicating with another computer. You are just thinking that it's on one system. Okay? And the OS That means the OS will make it transparent. And it can do the synchronization for you. So you don't have to worry about the Berkeley and Kristen algorithm to synchronize. Because the operating system itself is a distributed operating system, and it handles all this synchronization for you. Okay? We handle the memory management, which is distributed. We handle the storage management, which is distributed. The file system also distributed, but we do not know that it's distributed. Okay? So the operating system make everything transparent, including the protection and security. Of course, when we talk about distributed systems, we have to talk about security, because hackers can access into your system, because every of your system is on the internet. Internet is public space, right? So all these computers are exposed to threats that is driven by the hackers. The hackers can attack your network, because your network is not private. Is shared internet network. Okay, and the networking is, of course, is provided to you because this is a distributed operating system, so you can access any of the internet just like a PC. Okay, so these are the job that the operating system provide. Distributed operating system provide. And there are two types. One type is called network operating system. The other one is distributed operating system, and the difference is the system image and autonomy, meaning that autonomy means who is in charge. Okay, autonomy, that is the meaning of it. The distributed system has shared autonomy. Okay? And also the difference can be the fault tolerance capability. Okay? Distributed operating system has better fault tolerance capability. Okay, these are the different type of operating systems that we see: multi-processor OS, network OS, or the operating system, distributed OS that we talked about just now. Okay? So the multi-processor OS, okay, looks like a virtual uniprocessor. Okay, it contains only one copy of the OS, communicate via shared memory, single one key. Okay? Now this multi-processor actually run in distributed system, but it is transparent to the developer or the user, like you are looking at it like a virtual uniprocessor. And in fact, your cloud service looks like this. Okay, your cloud services that you use, let's say for example, you access Amazon or you buy the cloud service from Amazon, it's actually multi-processor. Okay? The network OS also does not look like a virtual uniprocessor. It contains multiple copies of it, and we are communicating using shared and run queues. Okay? So it's exposed, meaning that it's not transparent. Okay, distributed OS, it looks like a virtual uniprocessor, more or less, look like the first multiprocessor OS. But then it contains a number of copies of OS, which communicate among themselves using messages. So the difference between the first and the last is that it looks like one OS, but actually it runs on multiple OS. Just that it's transparent, you don't feel it. The first one, it looks like uniprocessor. Actually, it has only one processor, one copy. Okay, and the rest have to operate or do the task according to what the operating system commands it to do. Okay, that is all for today. Just my time. Somebody is already waiting on something. Okay, I'll see you next week. Some of you, I'll see you tomorrow. So that is the end of the first lecture. We'll go to lecture 2 next week. Before that, we'll go to sign.